Hi everybody, welcome back for part 2 of the 3.3 lecture video on the section entitled Power Functions and Polynomial Functions. In this part of the video, we're going to be talking about the local behavior of polynomial functions, and in the first part of the video, we talked about the end behavior of both power functions and polynomial functions. So now we're going to talk about x and y intercepts and also turning points and how those relate to the degree of a polynomial function. So you can see in the graph here of just some polynomial function. A polynomial function either rises or falls as you move to the left or moves to the right. And of course, it's going to cross the x-axis at some point. They don't have to, but in the case that they do, those places where you cross the x-axis are called x-intercepts. And wherever you cross the y-axis is called the y-intercept. And you'll notice that there are a couple places on the graph where the function changes from increasing to decreasing, which we call turning points. And you might remember from an earlier section, we could also call those turning points, or the y-coordinates of those turning points, local max and local minimum values. Okay. So we'll talk about, again, how x-intercepts and turning points relate to the degree of a polynomial, or what information they give us. So first, a turning point is the turning point of a graph is a point at which the graph changes direction from increasing to decreasing, or vice versa, decreasing to increasing. I just mentioned the y-intercept is the point at which the function has an input of 0. Of course, that's where you would cross the y-axis, and the x-intercepts are the points at which the outputs of the function are 0. And given a polynomial function, if we want to determine the intercepts, we can determine the y-intercepts by setting x equal to 0 and finding the corresponding output value for the function. To determine the x-intercepts, we solve for the input values that lead an output value of 0. So we'll start off here with an example, or a couple examples of finding intercepts of a polynomial function. And we'll start with part A. So we're going to find the intercepts of the function f of x equals 2 times, and then we have 3 factors, x plus 4, x minus 1, and x minus 3. Okay, so the y-intercept is going to be obtained by inputting the value of 0 into the function. So we get 2 times 0 plus 4 times 0 minus 1 times 0 minus 3. And of course, that becomes 2 times 4 times negative 1 times negative 3. 2 times 4 is 8. Negative 1 times negative 3 is 3. Okay, so we get 2 times 4 is 8. And of course, negative 1 times negative 3 is positive 3. And 8 times 3 is going to give us a y-intercept, or output, of 24. So we know this the graph of this function is going to cross the y-axis at the y value of 24. Now, for the x-intercepts, what we do is we take our function f of x, 2 times x plus 4 times x minus 1 times x minus 3, and we go ahead and set that equal to 0. And we have 3 factors here, x plus 4. So 2 is a constant factor. It does not involve x. So we identify the 3 factors, x plus 4, x minus 1, and x minus 3. And whenever you have a function that is in factored form and is equal to 0, our solutions will be obtained by setting each of those factors equal to 0 and solving for x. So subtracting 4 from x plus 4 equals 0 is going to give us an x value of negative 4. adding 1 to both sides of x minus 1 equals 0 gives us x equals 1, and adding 3 to both sides of x minus 3 equals 0 gives us 3. And there would be our 3 x-intercepts for this function, -4, 1, and 3. Okay, so now we'll do part B, again finding the intercepts, both x and y intercepts of the function f of x equals x to the 4th minus 5x squared minus 36. Okay, now this function is not in factored form like the one in part A. So when we get to finding the x-intercepts, we're going to have to factor this. But we'll start with the y-intercept. And again, the y-intercept is the value of y when x is 0. So y equals f of 0. That's 0 to the 4th minus 5 times 0 squared minus 36. And the first two terms end up being 0. So we get an output value of -36, and that's our y-intercept. Now for the x-intercept or x-intercepts, those are going to be obtained by taking the equation of the function and setting that equal to 0. Now, this is a 4th degree polynomial function, and you'll notice that if you kind of rewrite the x to the 4th term as x squared squared minus 5x squared minus 36 equals 0, you'll notice that the power of x in the middle term is being squared. So x squared is being squared in the first term to get x to the 4th. And what we can do is factor this by factoring it into two binomials that start with x squared. Okay, so we know that x squared times x squared is going to give us back that first term of x to the 4th. Now we're just looking for two numbers that multiply to -36 but add to -5, which I believe would be -9 and a +4. Okay. Now the x squared plus 4 has complex solutions, so that factor never equals 0, but we'll set each of these two factors equal to 0. Oh, sorry, I'm trying to skip a step. First, what we're going to do is factor this x squared minus 9, and that'll factor as x minus 3 times x plus 3. And then x squared plus 4 is not factorable over the real numbers, so that factor is going to stay. So we can set x minus 3 equal to 0, x plus 3 equals 0, and it turns out that x squared plus 4 can never equal 0. Okay? Not over the real numbers anyways. And then by adding 3 to the first equation and subtracting 3 on both sides of the second, our two x-intercepts end up being plus or minus 3. Okay, so this is a 4th degree polynomial that had two x-intercepts, and of course, a polynomial function always has a y-intercept. Okay, so now we're going to talk about the relationship between intercepts and turning points. Now first, some terminology that's going to be coming up for us at various times in this chapter is the idea of what a continuous function is. So a continuous function is one that has no breaks in its graph, which essentially means the graph can be drawn without lifting the pen from the paper. And furthermore, a smooth curve is a graph that has no sharp corners. The turning points of a smooth graph must always occur at rounded curves. The graphs of polynomial functions are both continuous and smooth. Now, in the box below, intercepts and turning points of polynomials, it turns out that a polynomial of degree n, or the highest power of x is n, will have at most n x-intercepts and n minus 1 turning points. So that means a polynomial function of degree n will never cross the x-axis more than n times and will never turn more than n minus 1 times. So, for example, what if I take this function in part A from our previous example, and I'm going to graph this in Desmos. Now, if you were to actually multiply this out, you're going to eventually get a 2x cubed plus or minus a bunch of other terms, okay, whatever they're going to be, but that's going to be your leading term. And that's because each factor has an x. X times x times x is x cubed, and the leading coefficient is 2. So this function is degree 3 and has at most 3 x-intercepts, which we found in part A as -4, 1, and 3, and one less turning point. Okay, it's not guaranteed to have 3 x-intercepts and 2 turning points, but that's at most what a polynomial function of degree 3 has. So let's graph this in Desmos just to confirm. There should be 3 places at most where we cross the x-axis, and 2 places where the graph is going to turn at most. So here's that function from part A of the previous example, and you'll see here from the graph that indeed it does cross the x-axis 3 times. So again, this function was degree 3. Okay, it has 3 x-intercepts, which was at the maximum number we could have. And you'll see me write these in blue. This function has 2 turning points, which is 1 less than the degree. Okay, so any polynomial of degree 3 has at most 3 x-intercepts and at most 2 turning points. It's just that this particular function meets the maximum possible number of x-intercepts and turning points. Okay, so let's go ahead and do an example where we answer that question. Now, the same function from part B, and by the way, this was supposed to be example 6, not 5. Okay, it says find the x-intercepts, and using those x-intercepts, what's the maximum number of turning points of the function f of x equals x to the 4th minus 5x squared minus 36. Now, this function f is a degree 4 polynomial, so it has at most 4 x-intercepts and 3 turning points. Okay, so that's what we get by that fact above. If a polynomial is degree 4, there can be at most 4 x-intercepts, although there could be less, and it'll have at most 3 turning points, although there could be less. Now, we saw that the x-intercepts of f of x were x equals plus or minus 3. So this function only ended up having 2 x-intercepts, but we were for sure knew that there could not be more than 4 of them, and there could not be more than 3 turning points. Okay. All right. And we could graph this in Desmos just to verify that. There should be 2 x-intercepts, but we'll find the actual number of turning points by looking at the graph. And we'll zoom in a little bit. You can see that we actually do indeed have 3 turning points, one of them being the y-intercept, but we only have 2 x-intercepts. So at most we could have had 4 x-intercepts, and at most we could have had 3 turning points. Okay, so this one met its maximum possible number of turning points of 3, but it did not meet its maximum number of x-intercepts, which, again, here we have 2, but there could never have been more than 4 x-intercepts. Okay, so continuing onward, say I want to find the maximum number of x-intercepts and turning points again from this polynomial function. Now you might want to put this in the general form first, where we put it in decreasing power order. So we could rearrange terms with -6x to the 8th being first, -3x to the 5th being second, 4x to the 4th being third, and there's a plus 3x and a minus 22. Now this is a degree 8 polynomial. So what that means, there's at most 8 x-intercepts and 7 turning points. Okay, so that's what there is at most. And again, just for fun, maybe we'll graph this function in Desmos just to see. We can just graph it and count the number of x-intercepts and turning points and see if we meet those maximums. All right, so here's that function graphed. Again, it's a degree 8 polynomial. Now, it had at most 8 x-intercepts, but you'll see this function actually never crosses the x-axis. So the maximum number it could have is 8, even though in this case there are 0. And you'll see here that there are actually 3 turning points, or in other words, 2 local maxes and 1 local min. So it was, we knew that it could not have more than 7, or 7 was the maximum number that it could have had, but it turns out having 0 x-intercepts and only 3 turning points. Okay, so again, the maximum number of x-intercepts was 8, which matches the degree, and the maximum number of turning points was 7, which is 1 less than the degree of 8, even though, again, no x-intercepts here and only 3 turning points. Okay. So a couple more, actually just one more example here. Probably should be number 8. Now, we started with the general form of a polynomial function, its equation, and we determined the maximum number of x-intercepts and turning points the graph of the function could have. Now, starting with the graph of a polynomial function, we can determine the minimum possible degree by finding the number of turning points of each function graph below. So, if whatever the number of turning points we find is, the minimum possible degree of the function would be 1 more than the number of turning points. So here in example 7, in the first graph, we'll notice that there are 2 turning points. Now there's actually 3 x-intercepts. Okay, but if there's 2 turning points, what that means is that the degree is at least going to be 1 more than that. The degree is at least 3. Okay, and as a matter of fact, because of the end here, whatever that degree is, it must be an odd degree because the graph rises on one side but falls on the other side of the graph. Okay, so 2 turning points, meaning that the degree is at least 3. It could be 3, 5, 7, 9. Because of the end behavior, it does have to be an odd degree polynomial function. Okay, now here's another graph of a polynomial function. And here what you'll notice is that this one has 1, 2, 3 turning points. So there's 3 turning points. Again, those also correspond to local max and mins. So the degree of this function is at least 4. And furthermore, because of the end behavior, we know that it has to be an even degree. So this polynomial function is degree 4 or degree 6 or degree 8. So it has to be at least 4, but we know that the degree has to be even because of the end behavior. The graph rises on both ends. So we'll conclude the video here. This last piece was just kind of to talk about the turning points and talk about, well, if we know the degree of a polynomial by its general form, we know that the maximum number of x-intercepts is the degree itself, and the number of possible turning points is 1 less than that degree. And starting with a graph of a polynomial function, you can count the number of turning points, and the degree is at least one higher than that. Okay, so we'll conclude here. Thanks for tuning in. Take care. Until next time, have a good one.